Okay, so last time here in BRIDGET dynamics, we we talked about finding the wave function of a friend. So we're trying to find psi for a particular probability that satisfies a particular probability that you will get a 1/32% chance or 1/32 chance, which is roughly 0.32, I believe, or it's some other value. I'm aware it's some other value. It's not just 0.32. But either way, very low chance of getting a girlfriend, right? Because of rejection, not rejection, all that shit, all that spiel. But yeah, and we constructed a wave function for him and his love states. At least try to quantize him. So up to that point, we have been preoccupied with the more complicated parts of quantum mechanics, but let's take a step back for this video and go back to the basics. Namely, to answer the question, what is a vector? What is a vector? We have always talked about like vectors, vector functions and states and eigenstates, eigenposition, stuff like that. In BRIDGET dynamics, when we took all those concepts from position theory, but we didn't quite answer in this course, what is a vector? Well, you could say it's an element of a vector space that satisfies, or it's a mathematical object that's part of a set that satisfies linearity and scalability and linear transforms. Like, I suppose if you add two vectors, it will result in a third vector that's also, or result in a third object, which is also a vector. If you scale it by a constant, that would also be an element of that vector space. And if I do a linear combination on that vector space, it's the same as applying a linear transform on that act we're doing on every single vector first. Some basic rules of vector space, but we never thought of vectors as just the individual objects. Now, of course, we have expressed them in terms of a wave function, but let's go back to the more discrete cases in this video. So today, we're going to be talking about where the KET vector notation came from. Where the heck this notation came from. And we will talk about a more discrete form of the fundamental fact that the integral from -infinity to positive infinity of the norm of a wave function with respect to x is 1. A more discrete case of that. So what the heck? Where the heck did this come from? So the answer to that question is from Paul Dirac. Very known physicist, came up with the Dirac relations, the Dirac equation, and if I remember correctly, he also, well, of course, he came up with this notation. Now, this is what we call a KET vector. KET vector, and let's make a new perspective on what exactly a KET vector is. Now, definition. A KET vector, which is this, is a row vector. A KET vector is an object. You say object. A KET vector is an object, which I will call A. A1, A2, dot dot dot, for n dimensions. Of course, when we're talking about theoretical physics, we generalize up to n dimensions, not just 3 or 4 dimensions. Although it could be confined to just 10 dimensions according to string theory. So it is an object that is expressed as a row vector, or a column vector. Sorry, column. This is is a column and this is a row. It's a column vector. Okay, so it's a little bit of math before we get into the physics of it. And then another definition, I'll just put into one definition. A BRA vector is an object. I would call it B, that is a B1, B2, that is expressed as a row vector. You may notice now that, oh well, it sort of looks eerily like a matrix. It's over here. This isn't really a vector. You cannot express it as you cannot really express it as an arrow in space-time. It would really just be a bunch of magnitudes. And we will see later why exactly it is expressed as a row vector. Alright? So we won't only be talking about Dirac notation, but we will also apply its applications through polarizing light, or should I say polarizing a person. But that will come a little bit later. Okay. So A, B. Now let's introduce a new operation called an inner product. What is an inner product? Oh, by the way, the entries over here is A1, A2, B1, B2 could be elements of the complex numbers. So I'll just add it here. Nope. So this A can be, or if I use the notation of modal logic, it's possible that A or B, A or B is an element of the complex numbers. Okay, so it's possible that A, B can be complex, and that we can take complex conjugates of these guys. So if you recall complex numbers, of course the complex number C is defined to be all numbers A plus BI, such that AB real and I squared equals -1. So I is the imaginary unit. And that if I have the complex plane, this is the real part and this is the imaginary part. If I have a vector over here, a complex number, A plus BI, the complex conjugate is just flipping the sign of the imaginary component. So this is the complex conjugate, A minus BI. That's the complex conjugate. Okay. And we usually denote it if Z is some complex number. We denote its complex conjugate as Z star. Okay. So a small verification of the complex numbers. Now, in the later part of the course, we will be applying construction of the complex numbers and making some isomorphism between that space and maybe F2 or RF space, RF2 space. So I think after like maybe tomorrow or some other day, I will derive an isomorphism between FR2 and complex numbers, and then make a new mathematical object from that, which we will study here in BRIDGET dynamics and how it applies to our physics. Okay, so KET and BRA vector. The reason why I name that is because, you know, BRA, KET. I know it's not very creative, but there's the names. As I said, you guys will see soon why exactly one is a column vector while the other is a row vector. Okay, so definition. Okay, suppose V is our vector space, all right? So I will call this object here, which takes V cross V and takes it to V, to be an operator on a KET and BRA vector. In V. So it's supposed V is not only composed of KET vectors but BRA vectors as well. So the BRA vector could act on the KET vector. So this operator is an operator on a KET BRA vector in V. So this object is called the inner product. Indeed, you'll see that this is very important because sometimes you take inner products between the wave function and itself and then take the square to find its probability, or the probabilities to take inner product of the wave function with itself to find the probability amplitude. So yeah, this is where it all stems from. So we have the inner product. It's called the inner product. And the inner product is basically a dot product between the two vectors we put into them. So it's a dot product between our KET vector and our BRA vector. Okay? So for a KET vector, which is A1, A2, dot dot dot, and a BRA vector, B, which is of course a row vector, B1, B2, dot dot dot. The inner product of this BRA vector and this KET vector is we just stick them together. So B, A, so the inner product between B and A is equal to the dot product. So we just add the products of each entry. So okay, so if this here are the ith entries and these are the jth entries, the dot product is the sum ranging for all I and j of the ai and bith elements, which is basically of course this will be limit of the natural numbers, counting numbers. So it would be A1, B1 plus A2, B2 plus A3, B3, and then dot 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 to keep it going. So now the inner product gives us a, it would give us a real valued function if these are the complex valued functions, of course. If one of them is real, it would give us still a complex valued function. And most importantly, this gives us the probability amplitudes, which we take the square of to obtain the probabilities themselves of with regards to what will happen to us, to a state, or to a system. Yes. So yeah. Just using the definition of a inner product, or we're basically using the definition of a dot product to define the inner product between a BRA and a KET vector. Okay. Now I don't think I need to explain what some matrices are because we're not really gonna dive much into matrices. But yeah. There's not really much. But we will develop a new perspective towards the time-independent Schrodinger equation. You know, there's A, V, a state V equals some eigenvalue times V. We will develop a new perspective towards this equation later. So let's dive into the physics. Let's go into the actual physics of it. So let's say, and what is this? Let's say I have a person over here. I have a human, regular, nice human, no gender just yet, or gender identity. And then I have a machine. That assigns this guy or this gal or whatever, this human being, with a gender. So it's a gender assigning machine. So once we make the person pass through this machine or have the person go through this machine, it would basically be identified or start identifying as a guy or girl. So it's gender identity, okay, not really the sex or the assigned gender at birth. So it's what they perceive themselves to be. Okay. And suppose I have a door that he cannot open on his own, but can only be opened by a machine that detects whether the person standing right in front of the door is a guy or a girl, according to their gender identity. So let's just hypothetically say that this machine can read the mind of this person, or the person dictates to the machine who exactly he or she is, right? So it can detect those, it can find information from this guy, whichever way it was. But the only thing that we want the machine to do is allow one gender to come through the door. So it's a detector. Now I'm not gatekeeping or anything. We will consider both cases, but just for the sake of simplicity right now, we will only be considering binary genders, male, female only, right now. Just now, maybe you guys can go ahead and find the probabilities for non-binary genders or others, or all that spiel. But let's say for now that we only have two binary genders, or we have the A gender, the bi gender. Okay. Gender identities, basically. Simple non-binary and the two binary genders. Okay, let's say we have those, and the machine assigns them, right? Either both genders, no genders, or male, female, and then we have a detector machine that only opens the door if the person identifies as a girl. So F. So F is required, and then I put the person through this machine. Let's put this person through the machine and have him present at the detector. And let's say that the person is turned into a male. What do you guys think will happen? Of course, the door would not open because the machine only allows gender or male identifying humans to pass through. So there's a 0% chance that the person will come through the door, or a 0% chance that the door will open fully, or that it will only open 0% amount. I'm not going to give the exact angle that the door will make with respect to the wall it's attached to, but it's just flat through. It's just flat out. Alright? Now, the same thing will happen if I turn this guy, or if this human is made into a human identifying as a girl, and then we have the machine detect or allow only male guys to pass through, not sexist by the way. Both of these guys, in both of these situations should not be sexist at all. These are hypothetical situations, regardless of the ethics. We're here for the physics, not the ethics of things, or how you feel about it. We're here for the physics of it. Okay. As much as possible though, when you're studying in LOS, try to detach yourself emotionally from these lectures. Like, don't take anything personal here. We're only trying to apply mathematics and physics to everything that we do here, or to what we see in the phenomena around us. Okay, so we're not objectifying anybody. We are not gatekeeping anything. We are not saying someone is invalid. Everyone is invalid in our university. Okay, these are just hypothetical situations. Okay, so same thing will happen. The door will not open at all, and there will be a 0% chance that this female or female identifying person will get through the door. Okay, so now let's say I have another one, having the person, and then I send them through the machine. Say it's a male, or let's do female also. Okay, let's say the machine assigns them with a female gender. They want to identify as a girl, and then we have another door with another detector. These two are independent rooms, okay? So that you cannot say that, oh, it's gonna be able to go through this door, it's gonna go through this door, or only this door. No, these are two separate or isolated cases. Okay, so this time the detector only allows females to enter. What you guys will think will happen to this girl over here? Of course, they'll be let through. So there's a 100% chance that the female will get through the door. Same thing happens when we have a bunch of photons, or maybe just one photon. We shoot it through a polarizer, right? It changes its orientation. So I have light, and then I have a polarizer. I have vertically polarized light, and then I have another polarizer that's vertical, that only allows horizontally polarized light to pass through. None of the particles will pass through the second polarizer because it is intrinsically vertically polarized. Likewise, if it is horizontally polarized and then I pass it through or try to pass it through a vertical polarizer, none of the particles will pass through. Right? Okay. Or well, if I make this another machine that's this one here, but it only accepts or is able to register or change, I guess, people of the same gender type or same polarization, as we call them, or as we call them. Yeah, same thing, same principle will work, will happen. Now what if, let's say, it is a broad spectrum, it is not only male and female, there are varying degrees of it, like there's a demi-male, demi-female, something like that kind of spiel. Well, of course, it would vary between 0 and 100%, the door opening or not. So it will happen half, if it is half male, half female, it will happen, or it may so happen that the door will only happen to open halfway, right? If it is either, right? Or if it is fully identified, or if the person is fully identified as both, then it will absolutely open regardless of what gender we assign it, or what gender we require it to only let through. Or if there's none, good luck to that guy, or to that non-binary person, because they won't be able to enter through any door that we make here, unless we assign the door to accept in agender people, right? Okay, so how do we confirm this mathematically? Well, vectors, as we've come to call them, are states. So we can express the polarization here, the first polarization as a vector. And it becomes apparent now that if I have the Schrödinger time-independent equation, or the time-independent Schrödinger equation, we have a new perspective because we can express the polarizers or the machine that assigns the gender as a vector. So we can now see that the matrix is not the experiment that we're going to perform on the state of the system, but in fact, it is now the states here, or these eigenvectors, that is the experiment. And it is that this Hermitian matrix, or this matrix over here, is the observable measure. It is the person. It's the person. My birds are having a discussion in the background, if you'll excuse them. And so, yeah, the new perspective on this equation is that eigenvectors. I'll just write down here. Eigenvectors equals to the experiment. The eigenvalue is the results. And the matrix, Hermitian or not, is the observable measure.
So this is our new perspective on the Schrodinger time-independent equation, or at least one of many. Okay.
So you will notice now that, oh yeah, okay. Let's first continue on with mathematically verifying that our intuition is true. Okay. Now suppose that the male state is the vector 1, 0, and the female state is the transpose of the female state is 0, 1. So now think of these two as the machines. This is the detector, this is the machine that assigns it, or the polarizer. Okay? Now, intrinsically speaking, this detector is made into F. If I take the transpose of this over here, this makes this a polarizer into a detector. Okay? So it could be the other way around, that we have this and we take that part with this. It would be the same thing. Or maybe, yeah, it would still be the same thing. We would still have the same results. So, to perform the experiment, mathematically, we take, this would actually just be equal to, the BRA vector, F. To perform the experiment, what we do is take the inner product between these two. So in fact, actually, we put this, we first polarize it into M, and we polarize it with F, or try to polarize it with F, or have it present to the door. So F, inner product M. Now, what do you guys think is missing here before we actually do the computation? Yes, we forgot to take the square of the amplitude, because if we don't take the square of the amplitude, we only end up with the probability amplitude, not the actual probabilities. Because if F and M here are indeed complex valued, we would still end up with a complex valued function. Or we cannot be certain that we have a real function and thus a real value. We can't have complex or negative. It gives a positive. We can have negative probabilities, right? Or complex probabilities. So that's why we take the square of the amplitude. I know it's still real, it doesn't matter. It would still be the same result as if we didn't take the square, but it's always important that you square the probability amplitude. Okay, so doing that, if we follow our rules a while ago, so it's 1, 0 dot 0, 1 squared is equal to 1 times 0 plus 0 times 1 squared, that's 0 squared, and that is indeed 0. Just like we said a while ago. We have it polarized in the M, and then we had it presented to the F. We get ourselves 0% chance of it passing through the door. Now let's do the converse case, wherein we have a congruence between the gender identity and the assignment we have to the door to which gender it's going to allow to pass through. So let's say this time this is also an M. I've only been focused with allowing females through. Let's let male guys come through this time. You guys can already see there's 1 times 1 over here, 0 times 0 here, add them, we get a 1. But let's do it anyway. So M squared to 1, 0 dot 0, 1 squared is equal to 1 times 0, 1 times 1. 1 times 1 plus 0 times 0 squared equals 1 squared is 1. And then let's do the female case in case some sexist tries to use this against a girl for some reason. F squared, same result, but we just switch the positions of the 0 and 1. 0. Sorry, this vector here is wrong. It's supposed to be 1, 0. This one's 0, 1. Okay, there. That's 0 times 0 plus 1 times 1. Now you'll be asking me, how can you prove that this operation is indeed true? Prove it to me. We'll just go to foundations. Go to foundations. And still 1 squared, still 1. Now, I will demonstrate to you guys why we square it in the discrete case over here. This is a discrete case. Let's suppose that the polarizer polarizes it to a vector -1. And taking its transpose somehow gives it an operator that isn't negative as well. So we end up with a product that gives us a negative probability amplitude. That's okay. The probability amplitude can be negative, mainly because we can take its square and end up with a real probability. Okay, so that's -1. So that's now -1 plus 0 squared. That's -1 squared. And now you realize that if we don't square it and just say, okay, this is the probabilities, it's a negative probability, negative 100% chance. What does that mean, right? I mean, we can certainly express negative values in physics in terms of motion. Like if say it's moving, if the vector is positive, it's moving forward. If it's moving, it's negative, it's moving backwards. If the acceleration is positive, it's the velocity is going up. If it's negative, it's going down, right? But when we're talking about probabilities, it can only really be positive because that's how our brains can only comprehend these kind of probabilities. I know there's probably an alien race out there that can probably comprehend negative probabilities, but we can only comprehend positive probabilities. We don't have any physical meaning to what exactly a negative probability is. So that's why we take the square. There's still 1. Same you realize that this is still the same polarizer. Still the same polarizer. Still vertical. Say this is vertical, this is vertical. The vector is pointed downwards, or sorry, it's an x, so it's going like this way. It's horizontally polarized, sorry. Horizontal. I mean, the vector is still this way, but you realize that the slit is always horizontal, no matter what you do, right? Now, we pass it through the detector that only allows horizontally polarized light to go through. Now, no matter what kind of vector you have, and its slope or inclination with respect to the y-axis is still 0, or with respect to the x-axis is still 0. It's still horizontal, so it will still certainly pass through, even though the vectors are practically in opposite directions. This over here is our detector. This over here is the polarizer, right? It's still horizontal. These guys would still be the same. They will not annihilate each other, and the math shows it. Okay, same thing happens with the girl, and just say replace this with F. Same result. Okay. Now, let's assume, next, an F range over some values. Because this is physics, we will be using degrees, not radians. 0 to 180 degrees. No, 360 degrees. Over some values, or if you're really math inclined like I do, it's 0 to 4 pi radians. We make sure to write radians so that it's not confused with, rad as a measurement for radiation amount or how radioactive it is, right? Okay. Now, so if we vision this like, if we think that M and F can range over some values now, let's say we can make it inclined to be somewhat feminine, somewhat of a female, but still somewhat a male. We can think of it as, as diagonally polarized light. Say it is half male, half female, bigender, maybe, or just halfway, half male, half female. You can think of it as some 45 degrees
polarized light, or light that's polarized 4 to 5 degrees. Okay. Now, I believe this is where we need to bring out our calculators. We do calculations. So if you guys have a calculator with you, it'd be better if you have a scientific calculator so that, yeah. And don't forget to convert it to degrees. Right now it shows degrees. It may show R, that means your calculator can interpret in terms of radians, so you always have to express it in terms of that. If you want to follow along with our discussion, but you prefer to use radians, definitely use this conversion factor. So 1 radian is equal to pi over 180 degrees. Okay, so if I have 2 radians, it is pi over 90 degrees. There, that's our conversion factor for degree to radians. If you guys want to continue along with this lecture but still use radians, but we will use degrees. Okay, so now our polarizer and our detector would be, so I have my x and y axis, which is principally m and f, because the basis vectors can be expressed as these guys. So, oh no, actually it's the other way around. This is f, this is m. Yeah. This is 1, 0, 0, 1. Right. So let's say I have a detector or a polarizer that is half male, half female. So, a polarizer P. And it forms a 45 degree, so just around half of it. So it's equal to both, okay? Let's get in some equality here. Okay, so let's say it is 45 degrees with respect to M, and it's still 45 degrees with respect to F. So it sums to 90 degrees as we intended it. It's equally both. Okay, let's zoom in on here. This is P. And this is the axis, the x-axis. Then actually the y-axis, this is x-axis, this is m, this is f. This is P. The dot product of P with x would, okay, this is theta here. This is basically just, basic basic trigonometry. And now since we're assuming the magnitude here is 1. It is a unit vector somewhat. We're assuming it's a unit vector, of course. But it would work the same way with any magnitude a or b or n that's natural or real. But you just have to multiply that, all right, to the vectors to get our converted or our real vector that we want to, play around with. Okay, so what we want to do with our P, in order to find the probabilities and play around with it, is we have to resolve it into its x and y components. Because primarily speaking, when we're working with these things, right, we are working in terms of the Cartesian coordinate system. But the vector that we are supplied with, P, or polarizer, is expressed in the circular coordinate system, or polar coordinate system, or spherical, but not really spherical because this is a two-dimensional space. So how do we resolve it into its vector components? Now it's just basic trigonometry, or now since our magnitude is just 1, it would be, so r. If I'm not wrong here, x, if a is the magnitude of a vector, x, the x component is a cosine theta, and y is a sine theta. Now since the magnitude of P we said to be 1, its x component is just cosine theta, and its y component is sine theta. Now the reason why it is cosine is because cosine over here, x component is this, how much we walk along the x direction, y component is how much we walk along the y direction. Remember SOHCAHTOA, cosine, SOHCAHTOA, sine is equal to the opposite over the hypotenuse, and Ka is cosine is equal to the adjacent of the hypotenuse. Now, sine theta is equal to opposite, which is y, over the hypotenuse. So you notice that if we rearrange this equation a little bit, multiply both sides by h is technically the magnitude already of the vector because it's the hypotenuse here, and this forms a right triangle. Okay, of course. And that gives us h sine theta equals y, and exactly this. A is just the hypotenuse in this case. It's the magnitude. Likewise, cosine of theta is adjacent, which is x, adjacent is the adjacent side, over the hypotenuse, which when you convert is h cosine theta is x. Just replace h with a because they're practically the same thing. H is a. It's not a close relation. It's exactly the same. So yeah, there. That's our derivation from cosine sine. So using these equations, we can derive that the x component of this vector, how much we run along here, is cosine theta. And here it is sine theta. So overall, when we convert our vector from polar to Cartesian coordinate system, P is equal precisely to sine theta cosine theta. Like, oops, cosine theta sine theta, sorry. Cosine theta sine theta. When theta is expressed in degrees or radians, we're going to assume it's degrees. So there is our vector. Of course, the transpose of P, which is just its KET vector representation, is equal to just flipping it and making it into a 1/2 matrix. Okay, so yeah, 45 degrees, so that would be cosine 45 and sine 45. Yeah, that should be right. You can verify it. 0 is 0.707. Okay, so let's use this P as an example. Its magnitude is 1. Magnitude is 1. So it's expressed as this order pair, 1, 45 degrees, in polar coordinates. So it's cosine, cosine 45 sine 45, which is precisely 0. I'm gonna round this up to 3 significant figures. 0.71, and our y is just the sine of 45, which is the same thing. So it's somewhere around here. It's not precisely 1, but it's close to it. And you notice it's the same. The x and y coordinates are symmetric. That's another thing that we need to note here, is that when we do have this over here, it should be somewhat symmetric. It is symmetric because it is the same angle. So therefore, because it is the same angle with respect to y and x direction, it would bisect it into two congruent lengths, right? If it has a different slope, one would be less than the other, one would be greater than the other. So it's a neat thing here. You guys could work out the proof for that, but I won't, because this is physics, and it would take us too long. Okay, 45 degrees, and then let's say that we pass it through the M detector.
So the person's polarized to a value of 0.71 and 0.71. That would be, yeah, half male, half female, but not precisely half, just somewhat half. You know, it's both are equal. Okay, both are equal. Okay, so let's pass it through an M detector. Let's compute that. So that would be the square of 0.71 times, and then male over here is 10 squared, and that's just 0.71 0.71 plus 0 squared. 0.71 squared is just ants times 2, 0.5. And there, that's our probability. 0.5, or if we multiply it by 1,000, it would give us 50%. And it is true. It has a 50% chance of opening. So the door will only open to a degree of 45 degrees. Or it would just open halfway. If it's a sliding door, it only opens halfway and then stops. Yeah. So this time, if it's expressed, or if the length can vary, it cannot just be one or the other, you know, I mean not length, but rather polarization, the door will open to a corresponding percentage, or will only open partially to some percentage of the total arc it will take to completely open the door. And you notice, yes, it is 50, because it is a combination of both the male and female in such a way where it doesn't exceed 1 in the probability. So indeed, we get a 50% as it passes through. Same thing with polarized light. If I make the polarizer or the detector to only allow, or if I polarize the light into 45 degrees, we get a 50% chance it will pass through. Okay. So yeah, that's 50%. 45 degrees bisects it into two congruent angles, and thus would probably be two congruent sides, right? Especially because it's both unit. If these two units or these two lengths would add up to 2, when you bisect it, it should cut it in half and have, you know, 1 and 1, which adds to 2. Right, makes sense. Okay, now let's make it unequal. Let's say that P makes a 70-degree angle with respect to X. Let's see now that P is equal to some 1 and then 70 degrees. Now, if we convert it to polar, that would be cosine of 70 and then sine of 70, which is, grab your calculator, that would be 0.34. Again, rounding up to 3 significant figures. And then sine of 70, 0.94. Now you notice, alright, we have a probability that's practically 1. So we need to find a way to kill it off, right? Kill it off in the end, so we don't get an exceeding probability. Okay, now let's say we pass it through the F. Let's say we pass it through the F detector. So that will give us the F state, or F BRA vector, P squared, gives us this over here, 0.34, 0.94, dot, and then F here. So it is 0, 1, so that's 0, 1 squared. And so that's practically just 0 plus 0.94 squared. That's just 0.94 squared and square your answer. Answer and squared. Oops. That's 0.94
88, which is 88%. And you notice that because it is polarized more, it's 70 degrees, it makes 70 degrees with respect to x, so it's steeper. So it is closer, it's closer to the F state. It's closer to polarizing it completely female, or making the person completely female. It's closer now, so it's very effeminate, still man, but it's very close to being transgender, or being a girl. So yeah. Because there will be non-binary people. They don't conform to basically male female, but they will exhibit some femininity or some masculinity. So this is the best way of finding out the probabilities of passing through that door. Okay, this assumes, of course, that the doors are instructed to open for M or F, and that the magnitudes are like that. You can vary it. All of these things are variable. Right? We can vary the magnitude of M and the magnitude of F. It cannot just be one or stuff like that. But for the sake of simplicity, we just made it like that. So indeed, we get a probability that's lower than 1. It's great. And it checks out. So 88%. So the door will open almost completely, but it would stop around 22% short of the entire arc. So 88% of the arc, and then stop by 22%. Near the end or finish of the arc. Okay. So after that, what can we conclude? So now you notice that these probabilities are 88% and all that stuff like that. And yeah. Now these probabilities make sense because these guys are a discrete case. These are discrete case of the fundamental fact that the integral from minus infinity to plus infinity of the norm of the wave function. Now if we think of these states as the wave function, but discretely, then the norm should, or the sum of the probabilities of the norm should equal 1, right? Or 100%. Now let's demonstrate that in the discrete case by having two people. So now we have two people, not just one person. We have two people, and then we make them going through the machine and then present to the detector. I have one here, and then I have another one here. Put them both into the machine. That makes them both male, or let's make this more interesting. Let's say it polarizes them to a masculine-ish, a non-binary person, or bi-gender person. And that would be giving us, I believe, it would just be, let's make it 13 degrees. And then we have them both present to the door, which allows males to pass through. Only males to pass through. So what will get out? So how many percent will the door open? Alright, let's construct the wave functions. Well, not really the wave functions, but discrete wave functions, or the states. So if I name this P1, it's P2. So P1, okay. Yeah, okay. So I believe the probabilities now, we would split it up into two, or a sum of probabilities. So yeah, I don't think this would exceed if they were both put into the same here. Okay, no. Instead of putting them both into the same machine, I will pass the other guy, through a polarization that makes it, let's say, 90 minus 13. So it's 77 degrees. And then I have them pass through M. There. That should equalize the probabilities. Yeah, when we do take the square and then stuff like that and sum it up. Yeah, okay. Alright, so this is very feminine-ish, and this one's very masculine. So it's closer to M, this one's far from M. Or, yeah, far from M. So that'll give us P1, or the state of P1 would be cosine 13 degrees, sine 13 degrees, and then P2 would be cosine 77 degrees, sine 77 degrees. And give us the following vectors. So bring a calculator again. 0.97, then sine 0.22. Let's make it 77, sine of 77, 0.97, and then cosine is 0.22. And you realize now, these are symmetric coordinates here. That gives us an indication that indeed it is some bisector that splits the x values. You have two vectors, they split it into some corresponding x and y values. Interesting. Okay, now that we have these converted into rectangular, let's pass them through the M detector. Then that gives us something 0.97, 0.22 dot, and then M is 10, so 10. And then, okay, and then that's, and let's say that these all exist in some probability space, okay? So our probabilities will exist in some total space. Okay, so yeah, that'll give us 0.97 plus 0 squared, which is equal to 0.97 squared, and then 0.97 squared gives us, wait, I'm going to use the precise values here. Cosine 13, answer squared, 0.95. 95% chance. So this guy's extremely close to being a guy, or being letting open. No, both of them will still not be able to go through the door, but the door will open up as much or very much for P1 than P2. That's what we want to prove, or want to show mathematically. And P2. So actually, this would be two sets of doors now. One for P1 and one for P2, because of course we cannot have one door and at two angles. So excuse me, this would actually be two doors. Okay, one for P1, one for P2, and then we want to find the total, stuff here. And we want to show indeed that even though these guys have different probabilities, so long as they're equal, we would get something that's 100%. The probabilities must add up to 100%. So this is a normalized. This is a normalized state already. And the function that we create out of them, these states over here, these wave functions, are actually normalized already. Okay. Okay, so P2 this time would have 0.22, 0.97, 10 squared. And then this time it would be 0.22 plus 0 squared, 0.22 squared should give us something that's 0.05. It should be something. Yes, indeed. It's 0.0484 if you approximate that to three significant figures that give us 0.05 or 5%, and this is 95%. And add up the probabilities, the total probability, so 100% is equal to P1, or sorry, the square of the probability amplitude, so the sum of the squares of the probability amplitude times 100. So with respect to one state, one vector, pi squared. Okay, and that's just basically 0.95 or the times 100. Sorry, this is times 100. Okay, there. If these are expressed in decimals, okay, 0.95 plus 0.05, which is, oh no, all that times 100, adds 1 times 100, which is 100%. So they all sum to 100%. So this is a discrete case of the fundamental fact that the integral from minus infinity to plus infinity of the norm or the square, the wave function, expressed in terms of x, with respect to x, let's move it backward, x infinity plus infinity will be 1. Indeed, checks out. So if I have a probability space or a sample space, not really sample space but probability space, which I will call V, the integral over all values of V, of all apples dt over V. So V is parameterized by T over here. T would be the time of V1. And since V over it would be the same as like sum, discrete sum. Because this, by definition of a Riemann sum, this discrete here, or this discrete sum over here should equal, or if you let the samples here, or let the probabilities get finer and finer, the limit, or their limit, as you know, we get smaller and smaller strips of rectangles, should be this integral over here. But this would sum over all of them. So we have an infinite amount of rectangles going either way. But this is just a discrete case over here. Okay. So let's state the fact in general, or let's restate over here. So for some samples Pi, for some systems Pi, the sum of it running through some polarizer or some other vector square must equal 1. And that if we take finer and finer stuff here, approximation or samples of these, it would converge to an integral. So make finer, and then we'll have the limit, the integral as infinity plus infinity with respect to t, the parameter, as the limit. There. So yeah, this is a more discrete case, and we went back to the basics, and this is a good place to stop.